Yeah, so I'm Giorgi Butbaia. I'm from University of New Hampshire, and today I'll be telling you how you can use machine learning techniques to essentially try to study smooth slice genus of a knot. So this is a project that started during this program with Fabian and Sergey. So all the things that you're going to see have been done in the past couple of weeks. So just to set up a brief overview of what we're going to be doing, so I'm just going to briefly introduce some basic facts of how you're going to try to motivate why the problem is interesting. I'm going to then briefly discuss the knot-Floyd homology, which is the main homology that we're going to use to actually try to encode all the invariants of the knot and use that as the input to the neural networks. Then I'm going to tell you about how we're going to construct the neural networks to actually try to model these model and predict smooth slice genus. And then we're going to address some issues that can be that we're going to encounter on our data set of knots, and then we're going to conclude by giving next steps. So knot is essentially just a formalization of how you can different ways of essentially tying a rope into a knot, and mathematically that can be essentially modeled as some kind of an embedding of the circle into S3 or sufficient nice three-dimensional space. And the usual knots are essentially the most famous, probably trefoil and other similar knots like this. Now, if you're a beginner to knot theory like yourself, then the most natural question you can ask is that you can form some kind of group structure on the set of all knots under whatever equivalence you might define on the set of knots, like say equivalence under isotopy type. Now the issue is that if you try to do that with the most obvious operation, it's not a group, it's going to be a monoid, with identity being the unknot. So that's essentially an issue. So then you can look at essentially what you can do, and you can notice that, well, knot is a trivial knot is essentially if only if it bounds a disk in the space it lives in, which is SP. So you can relax this condition by essentially looking at slice knot, which sort of tries to motivate, which serves as a sort of motivation behind the slice genus. So slice is essentially going to be thinking of the disks, but now disk being in the four-ball, which is going to be thought of as something whose boundary is going to be US3. And now if you think of the coefficient of the group of the monoid under this equivalence, which is called concordance, so two knots are equivalent to your connected sum by mirror and reverse orientation, is going to be sliced, then you're going to get something that is a group. So that sort of motivates, or one of the motivations behind considering something like a smooth slice genus. So essentially, just to give a formal definition, I think for the quantity that we're going to be studying is that smooth slice genus is going to be essentially the minimal genus of the disk that can be smoothly embedded in the four-ball, such that it bounds whose boundary is your knot. It's a smooth, proper embedding. And one of the other interesting things that it has is that it essentially is a lower bound to the unknotting number. And that unknotting number can be thought of as essentially how many times you can change each crossing from an overcrossing to an undercrossing and vice versa, and essentially the minimal length of the sequence of changing each individual crossing. And your four smooth genus bounds this unknotting number. So now to actually bring the motivation of why this is a complicated problem is that there's no known algorithm which universally allows you to compute slice genus for any arbitrary knot. It's can be done only on very special cases and can be done on essentially case-by-case basis. So the main motivation or main idea that we had was to essentially try to apply machine learning techniques to try to study the slice genus. So the goal is, as with any machine learning technique, you need to first define what's going to be the format or the encoding of the input of the neural network. And then you have to define what's going to be the output. Now, the input is essentially going to be just like as with any sort of way of studying certain kind of properties associated knot, we're going to study essentially take one of the knot homologies that we can consider for a knot. And there's two probably most famous ones that come to mind, which are homology, which is essentially categorification. Can be thought of as categorification of the Jones polynomial, which is associated to the knot, and knot-Floyd homology, which can be thought of as the categorification of the Alexander polynomial. So the idea is to essentially use these polynomials or non-polynomials in a certain way as an input to a neural network, and then try to essentially figure out a way to predict the smooth slide genes. So,
can I ask?
Yes.
Do you know that those homologies determine the slice genes?
No,
So
I mean,
why are you studying?
that's good. In general, we just want to see if there's any kind of stricter bounds that we can come up with than say Auschwitz-Szabo invariant or some other kind of lower upper bound for them to come up. There's no hope that we're going to exactly find a formula that takes, say, this polynomial and reconstruct the smooth slide gene. It's more so to understand if there's any kind of more invariants that are hidden or objects that can construct out of the homologies so that you can use these to then try to study or put stricter bounds on the smooth slide genus.
Could you also run correctly? It's just dimensional pattern.
The dimensional pattern as in what do you?
Well, just like a photograph.
Oh yeah, I mean that can be done. We actually tried that one as essentially just feeding the PD code of the knot and using that as an input. The problem with that was that the neural network was overfitting quite badly. The issue, and one of the things that I'm going to also mention here is that there's very few knots in the knot database that we're considering which have slide genus 0. And when it struggles the most, and I'm going to show that in a couple of minutes, is distinguishing slide genus 1 from slide genus 0. So that's where it struggles the most. And there's very few which are 0. So there's a couple of techniques that we're going to mention which are not perfect for this purpose, but at least they help in some extent to the neural networks to try to ameliorate this situation.
Just a related question. Did you try braid into G4?
Right? No,
No.
we haven't.
So having an int-to-int hasn't been applied to this yet?
No, we haven't tried into for this one.
Thanks.
But in principle, that's a good question because one thing that we're going to encounter is the defining permutation invariant neural networks and transformers some natural candidates for these. But we found that just using very simple neural networks work more or less well. I mean, obviously, there's no expectation that it's going to predict the slide genes perfectly, but at least to predict with some reasonable accuracy.
And Marquis was running, right? But I don't know what he gave us.
He ran braid to G4?
I don't think.
Yeah, that does sound right. Just without a, but no deep sense.
No, I think it was a no.
Right. So essentially, we're mainly going to focus on the non-polar homology. We tried both home-fleet polynomials and the Hager-Floyd polynomials, but found that it's essentially the non-polar homology has been producing better results. So we're just going to focus on that. I'm just going to briefly recall the non-polar homology. It's a very nice theory in the sense that you essentially consider something known as the Hager splitting into handle bodies of your three-dimensional manifold. And in this case, three-dimensional manifold where your knot lives is just a sphere sphere. And you can pick a very nice type of description, which is known as essentially the Hager diagram, which is a very nice combinatorial description of your three manifold, which you can model by essentially picking your genus G surface, picking your cycles, which essentially define your handle bodies. And by this, when you glue these handle bodies, they define essentially your three manifold. This is useful because you can construct a knot in a very simple way by picking two special points on your genus G surface, and then taking two curves such that one of them does not intersect your alpha curves and the other ones don't intersect your beta curves. And then once you merge this and then pull these curves into their respective handle bodies, you're going to get a knot. And this allows you to define essentially a Floer homology associated with this by noting that your genus G surface is going to be a Riemannian manifold admitting some sort of almost complex structure. And roughly the sketch is that you need to associate some sort of symplectic manifold. These curves allow you to define these sort of Lagrangian submanifold, and it gives you a natural setting for the Floer homology. Now, I'm skipping a lot of details here, but essentially the sense is that you have some sort of nice symplectic structure that you can define and then consider some kind of Floer homology. And the chain complex itself, and the reason I'm mentioning this is because we're going to be really looking at these two gradings that are going to show up in the polynomials as the degrees. And these two gradings will exhibit a certain kind of nice pattern that neural network actually captures that we'll observe in a couple of minutes. And another thing is that the Alexander polynomial has essentially, Alexander grading has this sort of nice relation of relating it to the Szabo invariant in some way. I'm not going to go into details, but I'm going to show the pattern that we're going to observe a couple of minutes and why this is going to be important. So point is that the input is going to be essentially the Poincare polynomial of the homology associated with the chain complex. And this is what we're going to use for the input of the neural network. With these two gradings that we're going to refer to as Alexander-Haskell grading. So essentially, to come back to the actual setting, we want to try to define a neural network which takes this Poincare polynomial of this homology and tries to predict G4. So we now have the input, and now we need to think of how we model the output of the neural network. So there's essentially, let me first, before describing the output is going to be just G4. And there's two different ways, either doing regression or classification. And what we found is that doing classification is much more effective for this problem. Second thing is that we need to figure out a way to actually input the polynomial into the neural network. And for this thing, we use deep sets construction, which is going to be essentially a permutation invariant neural network. What it means essentially is that there's no natural way to order these coefficients. Obviously, they're a summation of these, so it's polynomial. So you need to input these degrees, the Alexander degree, Haskell degree, and the corresponding rank of the homology as the input. And it essentially forms a set that you can use as an input. And the idea is very simple. It's to just construct a permutation, is to essentially split your neural network into two different parts. First, you use essentially individual networks, which learn these features corresponding to individual elements of the set. Then you sum up all of these and use that summation as the input to the other neural network. So just more precisely, it essentially looks something like this. And obviously, it is going to be invariant under permutation with the terms of your polynomial. Now, this captures the degrees, and obviously, if you have some coefficient in front, it's going to take into account by essentially summing that up. But we actually want to care about the rank of the homology, so we can just add the coefficient as the one of the terms in the inputs to the network, which learns these features corresponding to this collection of terms. So this essentially allows us to model or allow us to input these polynomials to the neural networks. And the next thing is essentially, as I said, to form a classification, formulate it as a classification task. And the reason for that is following. So we're going to be using some sort of data set, and maximal genus in that data set for maximum slice genus in the data set is 6. So we just essentially have neural network output 6 different components and use it as essentially as a classification task where each of the components is going to correspond to essentially self-maxing or the probabilities of the individual genus being likely candidate as the value for that given node. So as usual, it just gives us, we use the usual categorical cross entropy for our neural network with the usual one-hot encoding for the genus. And because the maximum is 6, it is well defined. And next, essentially to consider the data set or use it, figure out which data set we're going to use. And we use the not info data set, which includes values for the slice genus for the majority of the nodes up to 13, including 13 processings. And we use that to train the neural network. And here you can see this is our loss function for predicting all of the genera, all of the values of the slice genus. And the accuracy for overall accuracy is 95% for predicting the value of the smooth genus. Now, this initially can be a bit misleading because if you look at the confusion matrix, you'll notice that, well, in most cases, it is very easily able to distinguish if you have, say, genus 1 and genus 2 nodes. But it's very bad at distinguishing, say, genus 0 and genus 1 nodes, or being able to, it confuses or has a lot of false negatives and false positives when trying to essentially distinguish, tell you if your node is going to be genus 1 or genus 0. So in fact, only 56% of the slice nodes are correctly predicted as being essentially sliced. So that's a problem. So what we did next is first, and the most obvious thing you can do is to create an ensemble of neural networks. So essentially they are trained on different partitions of the data set with different random initializations, and you essentially combine it into this whole ensemble of neural networks and use that for predicting. Now, the overall accuracy only increases by 1%, so from 95 we get to around 96. But the interesting thing is that when predicting the slice knots, the accuracy just goes up to 70%. So it's now better, slightly better, at distinguishing genus 1 for genus 1 and for genus 0 from each other. So one other thing we can do is that, well, not all, as I said, although it is available for majority of the knots, it's not available for all of them. There's still some 13 knots with 13 crossing which don't have, for which the core genus is unknown. So we can do the predictions, and we, by doing so, we essentially get that couple of knots, for example, these are predicted with 99% confidence, and this confidence is actually confidence that the neural network thinks that this is going to be a slice knot or genus one slice, a slice genus equal to 1, a slice genus equal to 2 knots. So it essentially partitions this. And for majority of these, and after rerunning this on the multiple different random initializations, we get that these are mostly stable, except for these knots, 13, 39 non-alternating 8, 6, 3, and this knot here, where it's essentially not able to tell if it's genus 2 or genus 1. We will see that when we augment the data that the predictions will essentially fluctuate a lot for these knots, but for most of the other ones, it will remain essentially stable. Now, there's no way to actually know. I mean, as of now, it is unknown what's the actual smooth genus of these knots, so we don't really know if they are actually predicting these correctly or not.
Say again what the confidence means?
Confidence is essentially, if I go back to here, it's essentially the output of the neural network. It's essentially interpreting it as a problem.
After applying the solve max.
Yeah, exactly. That's exactly it. So it's not really a probability that it being this value, it's rather neural network that this is confidence. Yes.
Actually, what's the distribution of the known for genera in knots up to 2 crossings?
What's the distribution?
I mean, so you have max G4 is 6.
Yeah.
Among 0 through 6.
Oh.
How many
Go to
of
the
each?
confusion matrix.
Yes, here is the confusion matrix, and there's very few, actually I'm gonna come back to that. So essentially, there's very few which are genus 0. In fact, I think I have a number which says it's 500 and something, whereas genus 1 are 1,000, sorry, a couple of thousand, in the order of thousands. So it's very imbalanced data set. And that's the next section where we're gonna essentially try to combat this. It's not perfect, but it essentially tries to increase artificially the number of slice knots in the data set.
But you see, it didn't do a majority prediction. So the confusion, so the biggest data set is it's 1.6 times 10 to the 3 genus 1.
Yeah.
But the confusion matrix is not sort of indicating that it's just predicting 1. It's only predicting 1 to 4.
Same.
Yeah. So yes. So the next thing is essentially to try to visualize what the network actually tried to learn. And if you look at the average values of these, essentially average value of the comparative polynomials in the given for the given value of the smooth genus, you will notice that for slice knots, the indices or the degrees of Maslov and Alexander are essentially on the line. But as you keep increasing your genus, the two different lines sort of spread apart. And this is also captured by essential neural networks. So if you look at the saliency maps for genus 0, so this is the actual distribution of how the coefficients are distributed. And if you look what the neural network actually captured, it essentially captures some non-trivial combination, but all of the gradients or all the maximum contributions to making this decision that not as a slice lie on the same line that we see the distribution of. So it's sort of like captures the most obvious pattern that you can have in your data set of knots. And same thing occurs for higher genus. So for genus 1, genus 2, you can see that the saliency maps are nearly similar. So it essentially tries to capture the most obvious patterns that it sees, but some non-trivial patterns too, to be able to distinguish, because there's still some overlap between genus 1 and 0. And as an additional note, although we didn't, although I'm not presenting much of about complete polynomials, there's also a similar pattern that can be observed when you're increasing the genus to sort of two different regions sort of are spreading apart. Good. So now the main issue, as I was mentioning, is that the data set is highly imbalanced. So the number of slice knots in the data set are only 500, whereas the number of knots which have slice genus 1 are in the order of 8,000. So there's huge imbalance in the data set. So the idea is to essentially try to generate new slice knots from the known ones. And the most obvious way is to either do a connected sum or do a band sum of the knots. Now, the band sums that I'm going to talk about now are just going to be equivalent to the connected sums because I'm only taking single band. So this is essentially just the setup to try to consider more general band sums. But the idea is essentially the following. So for example, here is a diagram of a band sum of two trefoil knots. So you essentially pick a band randomly, you pick two knots, you pick which edges to cut, so that everything, so the orientation is going to be consistent. And then you essentially merge this and produce another slice knot if you have picked K1 and K2 both slice. So this is essentially just a brief overview of how this would essentially work. So we just take all pairs of K1 and K2, compute their band sums by picking a random band, and that compute the corresponding Hager-Floer polynomials. So by doing so, the accuracy is nearly the same of overall accuracy for predicting the genus. So it remains around 95%. However, the performance for predicting is slightly better in the sense that about 91% of slice knots are classified correctly. But this can be interpreted simply because as we added artificially much more number of connected sums, and because of this, it just predicts those additional knots slightly better. However, now it's more balanced in the sense that there's roughly equal number of genus 1 and genus 0 knots, and it is able to slightly perform better. And when looking at the predictions, the only ones that change are the ones where it was either unsure, or there's one exception here where the neural network was predicting this 100% certainty that this must have had slice genus 2, but it's now saying that it's unsure and it's predicting that its slice genus equals to 1, with some uncertainty, with it being only certain by 60%. Good. Another thing that can be tried is to essentially try to predict more or less recent result would be like try to predict for the Conway knot. So just removing the Conway knot from the training data set and try to see if it is able to actually predict that. And by doing the same technique and ensembling the neural network, you can see that it actually is able to predict it correctly, that its slice genus equals to 1. So that's essentially the main things that I wanted to say. So essentially, it seems that these neural networks seem to capture some useful patterns in the knot invariance. And the next steps are to essentially figure out if there's a better way to interpret the neural networks of what they actually learn, and essentially to try to fix all the issues like the lack of large number of slice knots, and try to see if there's a more better way of encoding the polynomials or the inputs to the neural networks. So that's all, and thank you.